These are Lesson 8.3 notes, Logarithmic Functions, Day 2. Today we're going to find inverses of logarithmic functions, and we're also going to graph and find the domain and range of logarithmic functions as well. To find the inverse of a logarithmic function, we have to remember that there's this relationship between logarithmic functions and exponential functions. Let's take the equation y equals log base 5 of x. In exponential form, this equation could be written with the base of 5, an exponent of y, and equaling x. So you remember we have the base is right underneath the log, our exponent's over here, and it's equal to this. I have not written the inverse yet. All I've done is I've transferred this equation, which was in logarithmic form. Now I've written it in exponential form. When we find the inverse of an equation, the easy thing that we typically do is we switch x and y. So whatever says x in the equation, we switch to y and vice versa. So in this equation, to find the inverse, I'm going to flip-flop. Wherever I see y's, I'm going to make x's, and wherever I see x's, I'm going to make them y's. This equation would become 5 to the x power equals y. And if you've got the inverse of a logarithmic function written correctly, it should be in the form y equals something. If you'd like to write it in that form so the y is first, you can do that. You'll notice that we switch x and y. Here's our equation, y equals 5 to the x power. We'll do the same thing with this equation, y equals log of x minus 5. You may recall if there's no subscript here for the log, we're using base 10. So you can write a little 10 in here. This is logarithmic form. Our first step is to get it in exponential form. Exponential form, here's our base, it's 10. Our exponent is y, and it's equal to x minus 5. We're next going to switch x and y like we did last time. So wherever we see y's, we're going to write x's. And wherever we see x's, we're going to write y's. The goal is to get y by itself. To get y by itself, we're going to add 5 to both sides of this equation. So if I add 5 to this side and I add 5 to this side, these 5's will cancel. I'm left with 10 to the x power plus 5 equals y. This is your answer. If you want to write it so it says y equals on the left side instead, that's fine. So the question is, how do you know if you've done the problem right? How have we done this problem correctly? Well, to see if we've done this problem correctly, let's bring our calculator in here. And the first thing I want to do is I want to try a value for x into the original equation. The original equation said log of x minus 5, so let's pick some number for x, say 8. And if we calculate the log of x minus 5, what we get is this decimal 0.47712125547, so on and so forth. If we've truly found the inverse of our equation here, what we should be able to do is take this answer, this 0.477 number, plug it in for the x here, and what we should get for y is what we plugged in originally to this equation, which was 8. So check this out. I'm going to do 10, use my caret feature, to this power, plus 5. And if I've done this correctly, I should get what I originally plugged in our first equation, which was 8, and I get 7.9, a whole bunch of 9s. That would basically, for all intents and purposes, give us 8. So I have found the correct equation here. We're going to try it one more time with a little more difficult equation. This says y equals log base 4 of x minus 3 plus 2. There is a little trick to this problem that you have to be aware of. We have a log base 4 of x minus 3. We're taking the logarithm of x minus 3. This plus 2 is not part of the logarithm. So anything that's not part of the logarithm has to be moved to the other side. Before I can write this equation in exponential form, I need to move this plus 2 away. So I'm going to have y minus 2. If you want to put that in parentheses, you can, or you can kind of think about it as being in parentheses, equals log base 4 x minus 3. Now we can write this in exponential form because we have our base, it's 4. Our exponent's over here on the other side, it's y minus 2. And this is equal to, in parentheses, x minus 3. All we've done so far is turned it from logarithmic form to exponential form. Now we switch x and y to find the inverse. So this y is going to become an x, 4 to the x minus 2 power, equals, this becomes a y minus 3. To get y by itself, we need to add 3 to both sides of the equation. These cancel, and when you're left, on the right side we have y, on the left side we have 4 to the x minus 2 power, plus 3. Now the 3 is not part of the exponent, so you just add it separately. So our final equation is y equals 4 to the x minus 2 power plus 3. Now let's graph some logarithmic functions down below here. And to graph logarithmic functions, we're actually going to use the inverse functions that we found up above here. So to graph the function y equals log base 5 of x, I'm actually going to suggest doing this first. Graph the inverse, which is y equals 5 to the x power. Now this is an exponential function. You can write it in the form a times b to the x power if you assume that there's a 1 out in front. So 1 is actually your initial value, and your growth factor is 5. So when we actually graph this function on our coordinate plane here, we can graph our initial value as the y-intercept at 0, 1. And then the next value is going to get multiplied. The y value gets multiplied by 5. It goes here. You recall from the other day that the x-axis is an asymptote. That's the line y equals 0. And that this function will very dramatically shoot up like this. Now this is not the answer. This is not y equals log base 5 of x. This is the inverse, y equals 5 to the x power. To graph the inverse, what we're going to do is a couple of things here. I'm going to take the inverses of these 2 points. Now we have a point here at 1, 5, and we have another point at 0, 1. The inverses of these values are 1, 0 and 5, 1. So we're going to graph the inverse points of the inverse graph. 1, 0 and 5, 1. Now another thing we're going to graph is we're going to graph the y equals x line. This is a line which reflects a graph onto its inverse. So the y equals x line is a line that goes through points like 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, and negative 1, negative 1, negative 2, negative 2, negative 3, negative 3. It goes through these nice diagonals, goes through these nice corners of squares. This helps me get a little bit better idea of what this graph looks like. The reflection graph is going to have an asymptote along the y-axis, and it's going to come up kind of like this. So it should be the same kind of curve as the original graph. This is a graph of the logarithm base 5 of x. So here's our log base 5 of x function. This is actually the answer to the problem. I'll circle this. This is sort of our answer that we're looking for right here. But I'm going to use the inverse function, y equals 1 times 5 to the x power, as a guide. So we graph the inverse function, then we take the inverse of these points to graph the logarithm function. Now what about over here? This one's a little bit more difficult. This was the original inverse function, so we're going to graph the inverse first. To graph this function, I may suggest plugging in a few points for x and y. If we plug in 2 for x, this would give you an exponent of 0. 4 to the 0 power is 1, plus 3 is 4. So I like to make this exponent equal to 0. So I'll plug in kind of the opposite of negative 2, which would be positive 2. So I'll plug in 2 for x. And then you can use your calculator. It's pretty easy if you want to do that. This should be something you should mentally be able to do as well. But if you need the extra assistance, it's as easy as doing 4 to the 2 minus 2 power, which should be 1, plus 3, and you hit enter and you should get 4. Now you should be able to do the same thing by plugging in 3 for x. 3 minus 2 is 1, 4 to the first power is 4, plus 3 is 7. This gives us a couple nice points. It's an exponential curve. It goes through 2, 4, 3, 7. This function is actually going to have an asymptote that's up 3 units. So you can kind of think of this being an imaginary line right here, and that this exponential function is basically hanging on really close to that line until it gets to this point, and it goes upward like this. Now our exponential function, this inverse function, goes through points like 2, 4 and 3, 7. Again, I'm going to graph the y equals x line. sort of my reflection line that will reflect a graph onto its inverse. Then I'm also going to graph these inverted points. So I'm going to take 2, 4, and 3, 7. I'm going to flip-flop the numbers. So 2, 4 becomes 4, 2. 3, 7 becomes 7, 3. Both of these points will become values on my logarithmic curve. Instead of this line at y equals 3 being the asymptote, now it's going to be a line at x equals 3. Kind of like you're flipping x and y again. And our graph is going to come up through here, through this point, curve around like this. This is your answer right here. It's this function right here. And you'll notice both of these exponential curves kind of behave differently than the exponential curves do. The exponential curves kind of start low and then they zoom up this way. The logarithmic curves zoom up and then they kind of level off like so. So you've seen examples of how to find inverses of logarithmic functions and how you can use these inverses to help you graph logarithmic functions as well. The last thing we're going to talk about today is how to find the domain and range of these logarithmic functions we've just circled. You may recall for domain is a list of all possible x values that this graph can go through, and I kind of think of a scanner as you're working your way from left to right. There's nothing, this graph doesn't start until I move all the way to basically right here, the y-axis, and just on the other side of the y-axis the graph starts. As you move from left to right, I see values that continue as I move from left to right to go on forever and ever toward infinity. So we say the domain is 0, infinity with both numbers in parentheses because the graph never reaches 0 and you can never reach infinity. So you can use this notation. You could also use the notation x is greater than 0, or you could use the notation real numbers greater than 0. The range, this arrow extends forever, downward, forever and ever and ever. So we say the range basically goes, the y values go all the way down to negative infinity. And though the graph is very slowly going to creep its way upward, it will creep its way upward forever and ever and ever, and it will head up toward infinity when we're done. So we say the range is from negative infinity to infinity, parentheses because you can never reach infinity in either direction, or you can use the term all real numbers. For the second function, the domain of this graph, you can see the graph doesn't really we don't really hit the graph until we hit 3. Just on the other side of 3, this graph exists. So if you want to say that the graph stretches horizontally from 3 to infinity, that's fine. There's nothing out here in this graph, but once we hit 3, once we get just beyond 3, then we can basically have any x value beyond that, like 4 or 7. The range for this function is the same range we had before. The graph stretches down forever and ever, and it will eventually climb upward toward infinity. So we say the range is negative infinity to infinity. If you wanted to use words, you could say x is greater than 3 for the domain. Again, for the range, you could say all real numbers. And that's how you find domain and range of these logarithmic functions.